an overview of system engineering. Jan, the floor is yours. Go ahead.
Thank you, Moni. Welcome, everybody. Before we start, can we just have 30 seconds of prayer, and we can continue? Thank you. So, give 30 seconds. Thank you very much. And then can I ask Yapi to address some safety aspects, for the 7-point safety aspects? Over to you, Yapi.
Thank you, Jan. I just want to mention the 7 basic general industry safety rules. If I can summarize, number 1, keep your work areas clean. A clean workspace makes it a safe working environment. Number 2, use a proper tool for the job. Using the wrong tool for the job can always result in injury or damage to the tool, which can lead to an injury. Number 3, never work on live equipment. For your personal safety, always follow proper lockout or switch off procedure prior to performing any maintenance or repair work on electrical equipment. Number 4, make sure chemicals are properly labeled and stored. Improper labeling and storage can lead to injuries or property loss due to fires or corrosion. Number 5, communicate hazards to other personnel. Never assume that the co-worker understands the hazard of a task, especially if they are new or new to the task. Number 6, stop work when needed to address hazard. Always stop work to take the time to get hazards and unsafe conditions addressed to make it safe to continue the task. Number 7, always wear the proper PPE for the work tasks. The lack of PPE or the use of improper PPE leads to many injuries in the workplace. PPE is the last line of defense when protecting yourself from the hazards of your work. If you come into contact with hazardous materials while not wearing the correct PPE, the injury will be more severe than if you were wearing it. Thank you, Jan. Over to you.
Thank you very much, Yapi. Today, I'm going to just give us an overview of systems engineering. It's a very wide field. So, based on everything that's available in industry and methods, we are also following the systems engineering process in Mozweli. So I hope I can just give us a short overview of what it is all about. I'm going to give a short background about systems engineering, the application of system engineering, the process application, just to touch on the functional aspects of safety of systems engineering, in the design process, the systems engineering functions, matrix project approach, Mozweli engineering, the life cycle of our projects. All these are attributes of systems engineering, the life cycle engineering process, requirements and verification, standardized specification practice, and then just an example of the systems engineering process. If we look at systems engineering, it originated from a systems approach where a system is defined by the functions that it has to fulfill within the boundaries, and the system is then defined of what's going inside and how it interacts over the boundaries. The whole systems approach has been applied then to engineering. It started off especially in the United States with their massive programs, and firstly in their military applications, because there are so many aspects of large programs that they have to look at, and this is just an organized way in which they did their military procurement. Since then, the whole systems engineering process and methods have been adapted also by NASA, the International the Institute for Electrical and Electronic Engineering. There are many handbooks and articles on systems engineering, and the International Committee for Systems Engineering in COSI. They log and they are the base for good practice in system engineering. But systems engineering has developed as a field, and many systems engineering methods and processes are available in theory from the academic side. Now, based on all these, we've developed our Mozweli way of doing this and applying everything that is available. Take from all of this information what will work for us and what is good practice. As we are not building space shuttles, as we are not building military equipment, we are building a nuclear reactor. There are specific, Mozweli specific factors that we have to look at. We are nuclear. Safety is important everywhere, but there is a big emphasis on safety in the design and safety in operations. Then systems in Mozweli, the nuclear process, nuclear reactor, is a thermohydraulic process compared to a space shuttle. The further in a nuclear reactor, we rely heavily on pressurized equipment and pressurized systems. So there's also the inclusion of the American Society of Mechanical Engineers good practices for a nuclear reactor, and the lifetime support over many, many years. It makes also a difference in nuclear compared to some short-lived military equipment. System engineering application. Systems engineering includes the system design and development. It is accomplished through the system engineering process, which requires appropriate application of scientific and engineering efforts to ensure that the ultimate product is operational feasible. I just mentioned some of the approaches in systems engineering. It's a top-down approach. It's a bottom-up build-up of components and verification that the whole system can work. It's life cycle orientated, and it's based on the identification and definition of system requirements and teamwork. So it's an interdisciplinary effort, and with the systems engineering approach, we can then define our system to have an operational plant at the end of the day. The systems engineering process application, as I just mentioned, we move from the needs that we've identified from industry or the needs from our people that want the nuclear power plant, so that we can fulfill those needs through the systems engineering process to an operational plant that we can maintain and operate for many, many years. The biggest principle of systems engineering is to break down the need into specifications of firstly the nuclear power plant. We analyze that all those requirements, and we break it down into smaller components, smaller subsystems, so that at the end we can build it up based on the technologies that's available to combine all the small systems and products into the operational plant at the end. During this process, we are making use of all our engineering disciplines to produce the end product at the end. So the systems engineering process works on iteration. Firstly, we have the user requirements specifications for our to comply with our needs. We break it down then into smaller systems that we can specify. After specification of all the subsystems through engineering, we break it then down into the final products that we have to build up, the subsystems and components to build up into the higher hierarchy of the nuclear power plant. So through this whole design process, it goes for the verification of firstly components up to subsystems up to the bigger system at the end to comply with all the requirements and needs that we defined in the beginning. If we just look at the systems engineering functional aspects, I mentioned that we define our system within the boundaries to define that section of a subsystem or the overall system in itself. If we can just touch, maybe the control guys will understand the mathematical breakdown of our main block, the yellow block. There are functions that our, in this case, say the complete plant has to fulfill. There are many inputs. I defined it with x1 to n. Then we have the functions inside our plant, and we've got certain outputs. In this case, we use the fuel. At the end, we have the electrical output. But that's also not just based on functions. We've got physical attributes. We've got plant sites. We've got the physical characteristics of buildings and the equipment itself to fit into a certain space. That is a static view that we have to break it down into the functions. At each of the functions, we break down further again to the same idea and to build it up again at the end. But on the other side, we also have to fulfill the dynamic requirements from our system. The nuclear power plant must be able to operate in certain modes, full power, 50% power on the one hand, and then also it must be down under maintenance. So we have to provide all the modes and transitions of our system through the different modes and states that it can be, to take that also into consideration in our as our main system. Firstly, the functions that I've defined then will then define our physical plant, and we've got mathematical simulations and the process design so that we can fulfill all the functions of the physical plant. But parallel to that, based on all the mathematical equations and the design of the plant, we also have the simulator with the control so that it presents in a mathematical way what is happening in our plant. So we differentiate between the physical plant and also the simulator. And there are many ways and verification, validation of certain simulation packages also available so that we can get as close as possible to reality with our simulation of our plant at the end, so that we have the confidence that what we do, especially in changing between different modes and states, that we can still comply with our final design. In our design process, we apply design concepts. It's in a normal way, we evaluate different options with respect to ease of access, maintainability, special tools, how to fulfill all the functions that we need to have the operational plant at the end. We don't demonstrate design consistency with results from risk reduction. We identify critical parameters and analyze the variability and solution sensitivity to variability. So we design the plant for a certain specification, but if something deviates, how sensitive are we for that? We identify the applicable process and material specifications. We design the system and process alternatives iteratively, as I mentioned before, and to allow for tolerances, because there are always tolerances that we can allow from mechanical process side to still be within our envelope. We adopt design solutions that facilitate fault detection, make it easy to operate and to repair or maintain at the end. We define the solutions to a level of detail that enables verification that requirements have been met. As I mentioned, the design is an iterative process whereby various concepts are evolved and evaluated against a set of requirements. Each iterative process shall be commensurate with cost, schedule, performance, and risk impact. The system engineering functions, as we mentioned in systems engineering, we define the functions. So I found it applicable to approach systems engineering with the systems engineering process and define it in some of the main functions. All the background information and documents sometimes is just a list of things that you have to look at in systems engineering, but I appreciate the differentiation of three main functions that we have. Firstly is for technical program planning and development. The technical program tasks that must be planned and implemented in the fulfillment of system engineering management. How are we going to manage it, and how can we interface with the project management, configuration management, data management, everything like that. I think the systems engineering process, that's a process that I've described, how we apply the definition of the system in breaking it down into smaller components and then building it up again into the main plant at the end. Then another function of systems engineering is the integration of specialty areas. That includes all the engineering disciplines and also specialist areas to build that into the mainstream engineering effort. The technical program planning, if I can go a bit further into that, that describes the technical program task that must be planned and implemented in fulfillment of the systems engineering process. And I mentioned here the program requirements, when are we going to write statement of works, of what has to be done. Program planning, work breakdowns, structure, schedule, cost projections, etc., based in close cooperation with the program management and program manager. Organization, producer supplier relationships, technical interface management, and very important part of systems engineering. Last week we listened to Tony about technical integration and interface management, program management, risk, safety, licensing, quality, and quality configuration control. And this is all based on, and we can only do the work with the right resources, which I'm going also to touch on. Then system engineering process, that's, sorry, the matrix project approach. How are we going to execute it? There are various models that they apply in industry. There's the project approach where each project have all the engineers under that project to fulfill a certain task. And there's also engineering that's driving projects, but in our case, one of the best models would be to follow the matrix project approach, where the project management takes the whole plant and systems through the life cycle to provide the system of integrity in compliance with all the requirements. How do we make sure that all the requirements have been met? We've got systems engineering where we define all the requirements, and that involves, as I explained, the breakdown and the build up again and verification. Then we've got engineering disciplines. All the engineering disciplines that I'm going to touch on after this to integrate that whole effort, as well as the engineering specialist areas. Now, the function from the engineering side is then to ensure that we have the correct technical integrity from all the engineering disciplines. That's about the quality of the designs, etc. While the project management, on the other hand, make sure that we do it in time and on schedule to have our system of integrity. From the side, we have then quality assurance, our configuration management, which is a critical part for the systems engineering process to define the documentation about all the equipment and the systems that we develop, so that it's described in the right documents. Just as I was talking about the simulation part, configuration management is the documented part of our system. It describes every component, all the subsystems, etc. Then we are linked to procurement. We have to interact with suppliers and vendors and subcontractors to procure the items and systems in time and to the correct integrity. And in nuclear engineering, we have the safety and licensing aspects that's also very important to build into our system. Mozweli engineering, I'm just mentioning some of the functions that engineering has to fulfill in our whole process. In systems engineering, as we've discussed now, is to follow and define the systems engineering process, make sure that the specifications are correct, its integration and interfacing, everything that goes over the boundaries of a system or a subsystem to make sure that we integrate and interface correctly. And the next one is then also we do the test verification and validation from the bottom up again to make sure that at the end we test our whole system, and from bottom up everything complies to first specification and and also in the operation functions that we require. Then a critical aspect of systems engineering in this process life cycle, we break it down into phases. So we compile baselines at every end of every phase so that we can manage it from that baseline for the next phase. Nuclear engineering and reactor physics, design neutronics models, fuel specification. So on the nuclear engineering side, there's a lot of work to be done. Process design, usually the chemical engineers, thermohydraulic process, chemical reactions and efforts, control philosophies. Electrical, there's also many specialist fields in electrical, low voltage, medium voltage, high voltage, etc. Mechanical, we've got systems and components, pressurized equipment, as I mentioned already. In the previous designs, we made use of the ASME, American Society of Mechanical Engineers, for pressurized equipment, piping and support, and equipment handling. On civil, structural, geotechnical, seismic, site, rain and water, etc. Control and instrumentation, our digital control system, instrumentation protection, also the safety protection systems, data servers and handling, and also we touch into metallurgy. There are other disciplines that are also involved: architectural, quantity surveying, geology, fire protection, town planning, climatology, environmental construction management. So we mention all the different specialist disciplines that will be involved in the design and development of the nuclear power plant. Supporting functions, there's also project management services, safety, quality assurance, health, environment, software and information systems, facilities, master data management and procurement. As I mentioned, one of the aspects of systems engineering is to find and divide the project up into a life cycle with certain phases. It's not very clear on this slide, but the principle is that we divide it up into many phases until completion of the project, but with baselines in between each and every phase from where we can manage then the next phase. The life cycle attributes between the project management and systems engineering, we define a life cycle process that we are going to use as basis for all the work that needs to be performed. It directs the engineering effort. We make sure that at the end of each phase that all the engineering actions have been integrated to conclude that phase. The life cycle process and all the actions that we perform in one phase defines then project management, planning and control, where quality assurance must step in. It gives on reporting a reference for design maturity, where we are in each phase can define and tell us how mature is our designs. As part of the baselines, we define all deliverables that are necessary at the end of each of these phases as a baseline for the next phase. This enables us, it enables the concurrent engineering effort so that we can make sure everything is included in that baseline. Per engineering activity, per engineering discipline, we define and interface then all the activities that's required for the engineering disciplines, their functional inputs, and so that we can make sure we've got an integrated design of integrity. We can review from baseline to the previous baseline that we've complied with all the requirements, and we conclude, as I mentioned, each phase with a baseline. From that baseline, we can then manage the change in the next phase. If we've made certain specifications that we cannot comply with, we can manage it against the baseline with a change process. The life cycle engineering process, I'm just touching on this in slightly more detail. We've got the preliminary phase that we are in now. We define the market needs. We have already defined the logical process and system. We've developed a concept system solution, and we compiled the broad design basis for the project. We cannot say that we've done everything because the broad design base is also dependent on the site that we will select. There would be some inputs required from the site. As soon as we've concluded then that we covered all the needs in the preliminary phase, we end that preliminary phase then with a good set of documents that describes the requirements for the nuclear reactor and then also for the next phase. During the concept design phase, we establish then the specific design basis. We go into more details. We define the system concept that is achievable. Then we go over to basic design. So if we can say it, firstly, if we can define it with specifications, we've got user requirement specifications here in the beginning, preliminary phase. Then we've got the system designs, the development specifications during concept design and basic design, and during detailed design, if we go into detailed design, then we compile all the system subsystem specifications and components. So it's a process of breaking down specifications and defining what we need in a way that we can produce it and manufacture it at the end. During manufacturing, we have various aspects that we have to look at. During construction, we establish the site and employ the team. We build all the structures. We look at the sequences, etc. During commissioning, we have cold commissioning, hot commissioning, and we also have then the interaction during all these phases with licensing. So before we can commence with one of these end phases, there are a lot of licenses that we need on our baselines to be able to continue to the next phase. Then operations, and at the end we also have the decommissioning and disposal then of our power plant. Then requirements and verification. I've mentioned requirements. One of the functions of systems engineering is requirements. There are defined specification methods that I'm going to touch on also just now. Usually in paragraph 3 of the specifications, we have all our requirements, where we define our requirements of what we need, what must the system be built in or designed in compliance with. But in our specification in paragraph 4, if we use standard specification practice of systems engineering, we define all the verification methods that we are going to use, and also in a cross-reference matrix. So for specification 1, it must be blue colored. How are we going to check that? It must be able to handle a pressure of a certain megapascals. How are we going to measure that? And how are we going to ensure that we have the right end product? As I mentioned before, so that we break our system down into subsystems, components, and at the end also the detailed small components. And from system, subsystem, component, it has a trail of specifications down to the lowest level. And in this verification that I mentioned in paragraph 4, for each component, how are we going to make sure that that component complies with the specification, how our subsystem complies with the specification, and at the end, how our whole nuclear MHD100 nuclear power plant complies with the specifications and needs that we addressed in the beginning. I'm not going to go in detail through all of these, but to use a standardized specification practice, I know from the beginning, especially from the MIL standards, they define specific specification types, and then there are minimum things that need to be included in the specification. They defined it, so it established a uniform practice for specification preparation to ensure that we include all the essential requirements and to aid in the use and analysis of specification content, so that we can make sure that we've captured at least all the requirements into each different type of specification. As I mentioned now, was that the type A specification is usually your system subsystem specification. It has just certain items that have to be included there. Then we got the development specification and product specification, and then there are also provision for material and process and material specifications. Pardon. Just a quick overview of the content. Firstly, we identify what we discuss, system overview, and the documents that describe the system. Usually there are documents that describe our system from our configuration management facility. There's requirements on our system. I'm not going to go through all the details, but we've got everything that describes our system's requirements in paragraph 3. Also modes and states, as I mentioned, system capability. What we are also including in here is all the what they call the LTs for the integration of producibility, etc. Design and construction, what is required there, electromagnetic radiation compatibility, product marking, so that we have the right project for the right product specifying linked to the right item that's on the shelf, workmanship, interchangeability, etc. And then what are our requirements with respect to documentation? We've got the logistics, as I mentioned, the utilities, maintenance, transportability, the supply system. Then There are certain procedures if we have clashing requirements, so that, for example, precedence is always safety in nuclear, then cost, schedule, etc. How are we qualifying these systems? And in general, we can have a pre-production or a standard sample that we can work from. Then, as I mentioned, paragraph 4, that defines how we are going to make sure that the product or the specifications that we've developed complies with all the requirements. We need special calculation, tests, examination, and all this is captured in a cross-reference matrix so that we can make sure that we've verified everything that we set in the specification. And then just some other notes and for the product that we want to develop. Just then I mentioned the process that we follow, just in more detail how we are doing it is, if we define the market needs, and there might be more into this, we determine the market expectations. We've got certain inputs, and then we've got the process output, so that we can make sure we list and capture all the needs and requirements in the first phases of the project. I just took a snapshot here out of the beginning of the project, everything that we need to do. Firstly, the needs, specific needs on a site, then policies, laws, regulation, etc. There are a lot of guides and good engineering practice that we can follow. So we define that in the beginning, and we list all of this in the documented process so that we know what we are doing, that we know we've captured everything. Thank you very much. So if there are any questions and answers, please speak to Mani about that. But on the side, I know we've seen a lot about the projects. So on the engineering side, I just want to demonstrate today that we've also got a good idea on where we are going and that we are busy with this. Thank you very much for the, I hope it's not too long or too short, and that we have some idea of systems engineering. Thank you, Mani.
Thank you very much, Jan, to share this very valuable set of thinking and approaches that we followed in our engineering environment, specific the system engineering, the do's and the don'ts. We're busy with that. We're doing that. As Jan mentioned, all these activities intertwine very closely to the previous two sessions that Anthony presented to us, the integration and interfaces, and there's many other intertwined aspects in the engineering environment. This particular one today was for the systems, the approach that we follow and the methodology that we followed in the engineering environment, for everyone to understand the basics behind the thinking and the doing of engineering. The plan of action is to follow next week with another engineering approach, maybe the bigger picture of engineering, that everyone understand what's happening in the world of engineering, in that wider spectrum of activities and tasks that needs to happen. Once again, thank you very much, Jan. For any questions, any comments, any feedback, any thoughts that anybody wants to raise, please approach it to myself as corporate at mozweli.com or mari.mountaineer@mozweli.com. Thank you very much for your time this morning. Much appreciated, and have a good and a blessed day. I will close down.
Thank you, everybody.